Okay, good morning, everybody. I hope everybody's doing well. Everybody's healthy and um, doing well this semester. Um, let's get started with the review for our second exam, which is going to be on Wednesday, October 28th, and it's going to happen within the time period of the lecture, the scheduled time for the class as the first exam. So it will be from 9:30 to 11 o'clock on Wednesday, October 28th. And as we did for the first exam, you will have an hour and a half to work on the questions. And then I'll give you 15 minutes, 15 additional minutes for you to put the papers and scan the papers with the solutions for your problems, and then you will upload those answers to your portal in Canvas. So in essence, the format of the exam is going to be the same as the first exam. So you will have access to the exam using Canvas. You will answer the questions using Canvas, and you will upload the files for some of the questions using also Canvas. So in terms of the material that is going to be evaluated in this second exam, so you have two sections. Let's talk about the format first. So in section 1, you'll have 10 true or false questions. These are going to be questions on the concepts, some of the concepts that we discussed in the second part of the class material. So that's going to be section 1. So 10 true or false questions, and those are going to be 2 points each. So a total of 20 points for the first section. And then section number 2, we're going to have 4 topical problems, short answer, explanation, description, mathematical. So based on what you have seen in the homework and in the labs, then the type of questions that you will be asked to answer in the exam will be similar to those. So you should expect a question in which you will perform some iterations of the simplex algorithm. Also, we have 2 methods for finding an initial solution for problems that have no initial solution because they don't have slack variables. So we discussed the big M method and the two-phase method. So for those questions, you should expect, for that material, you should expect at least one question per method. And I'm going to talk about those in a minute. And then finally, we have a question or a problem that is going to be associated to the sensitivity analysis. So let's look at the material. So in this part of the course semester, in this part of the semester, we look at lecture 4, which is the simplex algorithm. And we started, a piece of this lecture was started and was material for the first exam. So if you remember, putting the problem into the standard form, meaning that you are making all the constraints equalities, using slacks and using the excess variables, that was material for the first exam. For the second exam, we're going to be focusing on the actual algorithm. So how do you use the algorithm to solve a problem? So how do you use the elementary row operations, and how do you proceed if you have a minimization problem, and how do you proceed if you have a maximization problem? So in this part of the semester, we talk about the preview of the simplex algorithm, and also we discuss how to use the simplex algorithm to solve problems that have more than 2 decision variables. So when we had 2 decision variables, we were using the graphical method. Then we transitioned to problems that have more than 2 decision variables. And we explained that for those type of problems, you need to apply the simplex algorithm to find a solution. So that was the first part of or the first lecture for this second exam. Any questions about this? Okay, good. So the simplex algorithm. So the next part, what we did after we learned how to use the simplex algorithm to solve problems, linear programming problems, we implemented the simplex, or we basically use Excel, and also we also use Ample to solve problems using the computer. So the idea was to show you that there are software out there that you can use to solve linear programming models. So if you formulate your problem and you can implement those problems or those models into Excel, and you can solve and find the solution for your problem. However, Excel has some limitations. So if you're solving problems that have 200 decision variables, 200 constraints, which are relatively big problems. If your problems are about that size, then you can use Excel without problems. But if you're solving problems that have, I don't know, 1,000 or 10,000 variables, then Excel might not be able to solve those problems. So that's why we added the Ample part to this section of solving the problems using the computers. So you know how to use Excel, you know how to use Ample. I asked you to do some homework on that, and you submitted that homework. So for the purpose of the exam, I'm not going to ask you to use Excel to solve the problems, okay? Or use Ample to solve the problems. For that part of the lecture material is not going to be evaluated in the exam. So I'm not going to, again, I'm not going to ask you to solve problems using Excel. I'm not going to ask you to solve problems using Ample for the exam. However, it's important that you know how to use the computer to solve these problems, because as you have seen, for very small problems, if you try to solve them by hand, that typically takes you a long time. So the idea with you solving those problems is that you learn how the algorithm works. And then if in the future, like for example, I know if you go work for any company, you will have access to Excel. However, that's not necessarily true for Ample. Not all companies will have Ample in their software packages. But since you know how the simplex algorithm works, you can implement a routine on your own. Let's say using Java or using any computer software language. So if you know how to code and you know how the simplex algorithm works, and you don't have access to Ample, you can still implement the simplex algorithm using the material that you have learned in this class. So that again is under the circumstances in which you have a problem that is big and you cannot solve using Excel. So you have the option to use the material that we learned in class to implement the algorithm, let's say in Java or C++. But again, for the purpose of the material or for the exam, the Excel or the Ample component is not going to be material for the exam in terms of a question. And then after lecture 5, we transition to lecture 6, which is the artificial starting solution. So for this, we learned two methods, the M method and the two-phase methods. So the artificial starting solution, the idea for this is that sometimes you don't have access to the Slack variables, and when you put the problem into equation form, sometimes you have equality, sometimes you have greater or equal to constraints. So when you put the problem into equation form, you don't have an initial solution available. So that's why you need to use the artificial variables. So the artificial variables allow you to find that initial solution so you can implement the simplex method. And we learned two methods. the M method and the two-phase method. And these two methods are going to be evaluated in the exam. So I can ask you, for example, for the M method, I'm not going to ask you to solve a problem, complete problem, but I can ask you to complete some pieces of the iterations. Like for example, I can show you the problem. I can give you, okay, these are the first two tables of the M method, and I can leave some spaces in that table for you to complete. So that's the idea. And the same thing for the two-phase method. So I can give you a problem. I can start, I can show you some pieces of the first, second iterations, and then you should know how to complete those tables by looking at the problem and looking at the information that is already there. So I can, for example, ask you to perform the minimum ratio test for a Tableau. And then after that, ask you to identify what is the entering variable or the variable that is leaving. I can ask you to complete an elementary row operation for one row, or to identify what are the basic variables. So the idea is that I can ask you questions, or maybe ask you to complete specific areas of the tables, so you don't have to work with the whole thing. You don't have to complete, I mean, because we have limited time. So I know that if I ask you to complete the whole process, you're not going to have enough time to work on the exam. So the idea is you will have access to these pieces, and you just have to complete those areas that are empty in those tables. Does that make sense?
Yes, it does.
Okay, good. So that's the idea for the M method and the two-phase method. And then after lecture 6, we discussed the lecture 7, which is the sensitivity analysis. So we discussed the graphical sensitivity analysis for the right-hand side and the objective function. So what would happen if you make changes to the right-hand side of the constraints? How would that impact the optimal solution? Also for the objective function, if you want to increase or decrease, let's say, the price for a product, how would that impact the solution of your problem? And we did that for problems with two decision variables. So that was a graphical sensitivity analysis. Excuse me. And then for problems that have more than two decision variables, we proceed with the algebraic sensitivity analysis for both the right-hand side and the objective function. So again, what I want to focus on in terms of the exam, obviously I can ask you questions in terms of the concept for the true or false questions. I can ask you things like, what is the reduced cost? What is the shadow price? What is the dual price? Those could be questions of the true or false. For the purpose of the problems, my idea of a problem will be similar to the assignment that you have for this material. I'm going to provide you with a table for the sensitivity analysis for a problem, and I want you to use that information to answer questions. So my interest for this part of the lecture material for this exam is to understand or to see whether or not you can use the information from the sensitivity analysis to answer questions. So just like you saw in the assignment for this material, and I have that question as part of this review, so we're going to look at that one in a minute. But that's the idea. So in terms of the exam material, again, then you have the lecture 4, which is the simplex algorithm. You have the artificial starting solution, the big M method, and the two-phase method. And then you have the sensitivity analysis. Again, for the sensitivity analysis, I want you to focus on using the report of the sensitivity analysis, like the report generated by Excel, and then use that information to answer questions. So interpret the report, which is what I have here at the end. So how to prepare for the exam? I I encourage you to obviously to look at the lecture slides, the lab, and the assignments. So if you have a good understanding of how to solve the problems that were presented in the labs and the assignments, so you should be doing very well. And then the lecture slide is basically make sure that you have an understanding of the concepts that were discussed in class. So what are basic variables? For example, what is the total price? What is the reduced cost? All those concepts could be good questions for the exam in terms of the true or false questions. Instructions, the exam is going to be closed books and notes. So again, this slide right here in terms of the format and the instructions are similar to the instructions that you follow for the first exam, which I'm very happy because I didn't see anyone facing any issues. I was able to get all the exams and everything in order, so that was good. So again, the exam is closed book and notes. Link to access the exam will be available in Canvas. So on Wednesday, you'll go to modules and you will have access to the exam. For the problems, make sure that you clearly show your work and all formulas using the solution. So that will help me award full and partial credit for if you don't get the right answer. And but you show your work, then I can provide you with partial credit. In this case, true or false questions, you will answer using the computer. And then for the 4 questions or problems, you will upload a file. So as I mentioned for the first exam, you will have a link to upload a file for each one of the problems. But if you feel more comfortable just putting all the papers together in a single file and uploading a single file, that's fine. That you can do that as well. So you can either upload a single file for each one of the questions, or you can group all the answers into a single file and upload a single file in one of the questions. So I will accept both type of uploads. So for the questions, make sure that you work the solution in a piece of paper, and then you can take a picture or scan and upload your solution file to Canvas. And as I mentioned at the beginning of the review, you will have 15 minutes to upload the files. So at 11 o'clock, my advice is that you stop working at 11 o'clock and use the time after 11, from 11 to 11:15 to upload the files. The exam will close at 11:15. So some of you might see that 15 minutes is a long time. I encourage you to stop at 11 because you don't know. Sometimes the internet might not allow you to upload the files quickly, or so if you have enough time to do the process, then you should find everything working. So again, make sure that you follow these recommendations. And then let's see, do you have any questions about the format? I'm recording this review, so you will have access to the review. You already have access to the slides, but you will have access to the video also. So I here have some questions from the assignments that I just want to go over them in case you have questions. So in this first problem, we have a group of constraints here, and we want to solve the problem for each of the following objective functions. So this is coming from the artificial solution homework or assignment. And then you have this objective function, which is a maximization, and you want to solve the problem. So in the homework or in the assignment, you have the option to choose if you wanted to solve this problem using the big M method, or if you want to solve the problem using the two-phase method. So either way, you should end up with the same answer. For the purpose of the solution of this assignment, I am going to show you the solution for the big M method. So here we have the initial problem. So as you can see, row 0, we have the, well, first of all, we need to set up the problem into standard form. So you can see that for the first constraint, you don't have to add a slack variable or subtract an excess variable because you have inequality form already. And for this one, you have a greater or equal constraint. So you need to subtract an excess variable. And then, so you have x1. Sorry, I think I have something. So if you put this into standard form, and then you want to add a slack variable, so you will need an artificial variable for the first constraint. And then for the second constraint, you have 2x1 minus 5x2 plus x3 minus e1 plus artificial variable equals 10. So the tableau in this first part have the artificial variables for both.
Professor, just a quick question. Why
Yes.
did we add the artificial variable? I know why we subtracted the e, but I don't know why we added the artificial variable.
So the artificial variables are going to help you find an initial solution for this problem. You see, for these two constraints, we don't have slack variables. Typically, like if you find the problems that we solve for lecture 4, the simplex algorithm, if you look at those problems, you will find out that the constraints that we use for those examples always were less than or equal to. So when you have less than or equal to constraints, you always have access to the slack variables, and the slack variables provide you with an initial solution quickly. But that's not the case when you have constraints that are equality or greater or equal to. So that's why we I taught you to use the artificial solution methods, which are the big M method and the two-phase method, for the cases in which you have constraints that are equality or greater or equal to. So the idea is that you create these artificial variables, and those artificial variables are going to help you find an initial solution for your problem. So if you put, like, if you just put this into standard form, let me see. See, where's the pointer option? Like if you just put this into standard form, this is what you're going to have. And then when you set up the first tableau for the problem, your first tableau will be up to here. So what happened with that initial tableau is that if you try to find a set of basic variables to implement the simplex method, you will see that you don't have two variables with columns that are zeros and ones, right? So typically that's what we want to find to identify the initial solution of the problem. We need to find those columns that are showing you the identity matrix, and those columns are going to tell you what are the basic variables. But for this problem, and this will be the same for all problems that have constraints that are equalities and greater or equal to, you will not be able to find an initial solution for your problem to start the simplex method. So the idea with this big M method and the two-phase method is for you to be able to find an initial solution so you can apply the simplex algorithm. So that's why we add these artificial variables, because if you look at this piece of the Tableau, now we are setting up two variables that will have, I mean, not in the first iteration, but our goal is to set up these two artificial variables so we can have the identity matrix and we can identify those variables as our initial solution for the problem. So in the big M method, our idea is to find a coefficient that is high, is big, a big coefficient. So we can, a big coefficient that will be, in this case, subtracted from the objective function. So we can find an initial solution that is going to eliminate the artificial variables out of the solution as quickly as possible. So if you put this big coefficient, and what this is going to do is you are going to, if we choose M as our, if we choose M equals 100, we're going to subtract those artificial variables from the objective function. And that's why we have these coefficients here. We want to subtract them from the objective function because we know that if we increase R1 and R2, that's going to impact our maximization negatively, right? So we want to make sure that we use the artificial variables only to find an initial solution. And the way we do that is by penalizing them in the objective function. So that's why we have this big M coefficient, that's 100 in this case. I choose that as, I mean, you can choose 1000, it's not going to make a difference as long as this number is big enough when compared to the other coefficients. So we are penalizing those artificial variables in the objective function because the idea is we want to use the artificial variables only to get an initial solution, and then we don't want to see them anymore in the problem. So what we are doing here by setting up the Tableau in this form, so we are subtracting, because we are maximizing, we are subtracting those artificial variables from the objective function, and we are also adding those artificial variables to the constraints. I'm sorry. So let me do that. So this is plus R1 plus R2, and this is going to be equal to 7, and this is going to be equal to 10. So at this point, we want to set up the initial Tableau. So we do that using the coefficients in the objective function. So 2, 3, 5, minus 100, minus 100. So when you put that into the first row, row 0, you know that you have to use the negative sign because you're moving them to the left side of the equation. So that's 2 becomes -2, 3 becomes -3, 5, -5 becomes 5. And then -100 becomes 100, and -100 becomes also positive 100. And then the coefficients of row 1 and row 2 are the coefficients from these two constraints. So up to this point, the only thing we have done is we have added artificial variables to the first constraint, the second constraint, and we are penalizing those artificial variables in the objective function because we want to use the artificial variables only to find an initial solution, and then we don't want them to appear anymore in the basic variables. We want them to be 0 at the end of the problem. So at this point, we're almost ready to apply the simplex method, but we always have to remember that the columns for the initial solution they have to look like this. They have to be zeros and one. So when you look at this problem and this first table, that's not the case. You have 100 in row 0 for R1, and you have 100 for row 0 in R2. So before you apply the simplex method, you have to make sure that those coefficients are equal to 0, which is what we are doing in this second table. We're making this coefficient 0 by applying the elementary row operations. And then on the next table, we are making this coefficient 0. And that's what we did up to this point. Okay, so at this point, we have our basic variables, R1 and R2. And if you look at this, you have the identity matrix right here. So right now we are ready to implement or to apply the simplex algorithm. So how do you proceed with the simplex algorithm? At this point, you're maximizing. So you're going to look for the largest negative coefficient to decide who's going to enter. So that will be this one. And then you perform the minimum ratio test to identify who's going to leave. So it's going to be R2. And then you proceed as performing the elementary row operations. So after entering X1 and performing the elementary row operations, X1 is here. So you can see here is zeros and ones and zeros and ones. So those are your basic variables. You check row 0 again to see if you still have a negative coefficient. And the answer is yes. The largest one is this one. So X2 is going to enter. You perform the minimum ratio test. And you see that for this one is 2/3 1/2. So that's 1 equals to 1.75. If you try to perform the minimum ratio test for this second variable, is 5/-2 1/2 or 2.5, -2.5. If you try to do the minimum ratio test with a negative number, it's going to be undefined. So that's why we don't take that into account. The minimum ratio test has to be positive. So if it is undefined, then that's not an option. If it is negative, it is undefined, so it's not an option. So that's why we only have this artificial variable is leaving. X2 is entering, so X2 is now part of the basics. And if you perform the elementary row operations to make this column zeros and ones, which is what we did here, then you'll see that there's no negative coefficient anymore. So you have found the optimal solution for your problem, which is X2 equals 4/7, X1 equals 6 with 3/7, and the objective function equals 14 4/7. And that's the solution for your problem. So again, the most important part when you are applying the big M method or the two-phase method is that you know how to add these artificial variables, so you know where to place them so you can find an initial solution for your problem. And then after you set up the initial tableau, you make sure that for those artificial variables that you have selected as the initial solution, that the columns reflect those values that are supposed to be reflected in terms of being zeros and ones. So like we did in here for R1 and R2, we needed to make sure that these values were zeros and ones. So that was not the case. So we needed to perform those elementary row operations to make those coefficients in row 0 equal to 0. And after that, then we can apply the simplex algorithm.
Professor, I have a question.
Yes.
Yeah, can this whole tableau be solved by using Excel?
Can this whole tableau can be solved using Excel? Yes, it could be solved using Excel.
Okay, starting from the big M all the way to the simplex algorithm, right?
Yeah, so basically the big M method is going to be it's not, Excel is not going to tell you I'm going to use the big M method. It will do it automatically. It knows that you have to add the artificial variables, and it will do it automatically.
Okay.
Yes. So as I mentioned at the beginning of the review, the idea for me to teach you these methods is that I know that you can now use Excel to solve the problems. However, Excel has some limitations. It will not solve problems that are big, more than 200 variables, for example. So if you end up going to industry and you don't have access to AMPO, for example, or you don't have access to any other software that can solve linear programming models, the only software that you have access to is Excel, and you find out that you cannot use Excel because your problem is bigger than 200 variables, then knowing how the algorithm works, knowing how the simplex method works, knowing how to find an initial solution when there's no slack variables, knowing those details will allow you to implement the simplex algorithm using code, using Java, using C++. So that's a tool that you have access to. So if you end up in that situation, you can still implement this algorithm using any language that you're familiar with. So that's the idea. And then for the second part of this problem, we have the same, instead of having a maximization, we have a minimization objective function. So you proceed in the same way. The only difference is how you set up the coefficients of the I'm sorry, how do you proceed in terms of deciding who's entering and who's leaving? So at this point, you see that this tableau is the same as the previous one. So you have minus 100, minus 100 here. So let's go back here. Let me set up this in standard form. So this is going to be the same. So it's x1 plus x2 plus x3 equals 7. This is the standard form, and this is going to be 2x1 minus x2 plus x3 minus e1 equals 10. And then, since you are minimizing, instead of subtracting the artificial variables to the objective function, since you are minimizing, the way to penalize the objective function by adding with the artificial variables is the opposite. So instead of subtracting them, you are going to add them. Minus x3 plus 100 R1 plus 100 R2. So just think about it. So if you're minimizing and you want to penalize these artificial variables, the way that you are going to penalize them is by increasing the objective function. Since the objective is to minimize the value, if you want to penalize the artificial variables, you want to increase the value of the artificial variable. So that's why we add the 100 instead of subtracting it. When you are maximizing, is the opposite. You want to make this value of z as big as possible. So the way you penalize the artificial variables is by subtracting them, because that's going to go against your objective. Okay, so the artificial variables, when you add them to the objective function or subtract them, they have to go against the objective function in order to be penalized. So that's why when we look at a minimization problem, the objective function is going to add the artificial variables. So when you set up the initial tableau, that's why these coefficients are going to show as negative, because if you remember from our initial discussion of the simplex method, what you do is that you move everything to the left, 3x1, 3x2 plus 5x3 minus 100 R1 minus 100 R2. Okay, so if you remember that discussion from our initial discussion of the simplex method, we move all the coefficients to the left in order to set up the row zero. So that's why when you look at the coefficients now, you have -2, -3, +5, -100, and -100. And that's row zero for this table. Let me take this out of here so you don't get confused. So that's our initial tableau. -2, -3, 5, 0, -100, and -100. That's coming from the objective function. And then the coefficients for row 1 and row 2 are the coefficients for the constraints with the artificial variables. And you can see now, as we did for the previous example, we have to make these look like the identity matrix. So we need to make -100 equal to 0 and -100 equal to 0. So that's what we are doing here for the first tableau. We're making these zeros and ones. And then for the second tableau, that's what we did. So at this point, we can apply the simplex algorithm. And since we're minimizing, we are gonna look for the largest positive coefficient, which is x1. So x1 is going to enter. We perform the minimum ratio test. 5 is the smallest value. So that means that x1 is going to enter and R2 is going to leave. So on the next iteration, sorry, this should be R2, sorry, R1. This should be R1. So you see here we have X1 and R1. Those are our basic variables. So at this point, we check if there's any positive coefficient in row 0. The answer is yes. So we choose the largest one, which is X2. We perform the minimum ratio test. And this guy, R1, is leaving. So now X2 is going to be basic. And X1 is going to be basic. So this should be X2. Sorry. This is X2. And at this point, we check again whether or not we have a positive coefficient in row 0. The answer is yes. So X3 is the largest one. So X3 is going to enter. We perform the minimum ratio test. This guy is leaving. So now X3 is going to be part of the basics. So you see, after performing the elementary row operations, that these two are the basic variables. And we check again whether or not we have a large or a positive coefficient in row 0. The answer is no. So we have found the optimal solution for this problem, which is X3 equals 4, X1 equals 3, and the objective function is equals to -14. So the same problem, just the only difference is that in one you're maximizing, in the other one you're minimizing. Any questions? Okay, so on the, let's see, what's the next one? So in this one, I think this is just for concept perspective. Like in this problem, you needed to look at this group of constraints, and the problem is going to tell you, okay, this is for phase 1. you need to write the objective function for phase one for the two-phase method, and you will have an objective function. And then you have to, for example, here, you are going to choose 1, 3, and 4 as the constraint for your problem. So here we're going to choose 1, 3, and 4. So the idea here is that you look at the constraints and you can identify how many artificial variables you will need to formulate the objective function of phase one for the two-phase method. So you know, phase one in the two-phase method, the objective function for phase one is always minimization of the sum of the artificial variables. So for this first part, we have a equality, we have a less than or equal to, and another less than or equal to. So we don't need artificial variables for these two constraints. We don't need them because those are less than or equal to constraints. So you can use a slack variable for both of them, and that those slack variables can help you find an initial solution. But that's not the case for this one. So you will need an artificial variable because this is an equality. So if you were to formulate the objective function for this first part, then the answer will be the minimization of R equals R1, because you only need an artificial variable, one artificial variable for this problem. If we proceed with the next one, let's see. I'm going to take this. So in this case, we're going to choose 1, 2, 4, and 5. Okay, so 1, 2, 4, and 5. So what is the, so we need an artificial variable for this one. We also need an artificial variable for this one because it is a greater or equal to, so there's no slack variable there. And then for this one, we don't need, because this is a less than or equal constraint. But for this one, we need an artificial variable because it's a greater or equal to constraint. So in this part, we need 3 artificial variables. So the objective function, again, it doesn't matter if this is maximization or minimization. The first phase of the two-phase method is always minimization. And you are going to need 3 artificial variables here as the objective function for phase one. Okay, so let's do one more. Let's do this one. So minimize z equals 3x1 plus 6x2. What are the constraints here? This is 3, 4, and 5. So 3, 4, and 5. So we don't need an artificial variable here because we have a slack. We don't need an artificial variable here because we have a slack. But we do need an artificial variable here because this is a greater or equal to constraint. So the objective function for this problem is going to be just R. So if you look at the solution, maybe the number, like here we have R1, R2, and R5. So the problem or the solution is using the number of the constraint to name the artificial variable. You don't necessarily have to use that naming process. As long as you can identify the number of artificial variables and you name them differently, then that will be enough. So I hope this makes sense. Any questions? Okay, so we have another problem here related to this two-phase method. This one says write phase one for the following problem and then solve to show that the problem has no feasible solution. So let's look at the solution for this problem. We have maximization of 2x1 plus 5x2 subject to these two constraints. So first, let's set up this constraint into standard form. So we have 3x1 plus 2x2 minus e1. And then we are going to need an artificial variable here, r1 equals 6. And then we have 2x1 plus x2 plus s1 equals 2. Okay, so those are the constraints in standard form. So when we set up the first phase, we only need one artificial variable, r1. So that's why our objective function is the minimization of r equals r1, subject to 3x1 plus 2x2 minus e1 plus r1 equals 6, which is this constraint right here. And then 2x1 plus x2 plus s, I name it s1. You can, I mean, just to be consistent, I'm going to change it to s2. So 2x1 plus x2 plus s2 equals 2. So those are the constraints, and that's the formulation of the first phase. So when you set up this into this tableau, again, we need to make sure that our tableau is consistent. So R1 is a basic variable, S2 is a basic variable. So when we look at this, we need to make sure that this coefficient is equal to 0. So the first elementary row operation is going to be for R1 to make R1 equal to 0. That's what we did here. So R1 is 0, 1, 0 now. And at this point, we can implement the simplex method to solve phase one. So we are going to look for, since we are minimizing, we're going to look for the largest positive coefficient. So that will be x1. And then we perform the minimum ratio test. So that means that S2 is leaving. So after performing the elementary row operations, we make this 0, 0, 1. So those are our basic variables. We check if we are done. We still have a positive coefficient here, 1/2. So we can enter x2. And we perform the minimum ratio test, and this guy is leaving. So we are entering x2, and x1 is leaving. So that's what we have here. And then we have this and this as our basic variables. But at this point, we're done. There's no other positive coefficient in row 0. So we have found the optimal solution for phase one. The question now is, or the problem, what the problem is asking is, write phase one for the following problem and then solve to show that the problem has no feasible solution. How do we know if this problem has a feasible or unfeasible solution? The question lies in the use of the artificial variables. So if you remember at the beginning of our discussion for the artificial methods of finding an initial solution for your problem, we want to use the artificial variables just to find an initial solution, but at the end, we want to see them leave the basic variables. We don't want them in the basic variables because we are just using them to find an initial solution so we can solve the actual problem, the original problem. If we solve the first phase and we have an artificial variable in the basic variables, which is the case here, R1 is still there. R1 is a basic variable, and we have found the optimal solution for the phase one. Since R1 is still there, and R1 is not 0, which means that the artificial variable has a value that is different than 0. You know, when the variables are non-basic, they're always equal to 0, right? So if they are non-basic, they're equal to 0. But if they are basic, then they assume the values that are shown in the tableau. If we end up phase one and we have a basic variable that is an artificial variable, then most likely this problem is infeasible, has no feasible solution. The problem is that if for you to find an initial solution of the problem, you still need the artificial variable to show a value, then that means that that original problem has no solution. Typically, what you will see when the problem has or you're always going to see when the problem has a feasible solution, those artificial variables are going to be out of the basic variable or the basic set when finding the optimal solution of phase one. That's not the case in this one. If you look, R1 is here and it has a value that is different than 0, that means that this problem has no solution. Okay, so there's no way that you can solve this problem. We can check with the constraints. You can see the constraints of this problem. You have a constraint that is less than or equal to 2, and then you have a constraint that is greater or equal to 6. If you try to find an x1 and x2 value for this problem that will satisfy both constraints, you will not find it. Okay, you can try. Let's say we use x1 equals 1 and x2 equals 0. X1 equals, when x1 equals 1, then it's going to be 3 times 1 plus 2 times 0 is going to be equal to 3. So it's not going to be greater than 6. But if you use 2 times 1, which is the second constraint, then you have 2, and 2 is less than or equal to 2. So you can satisfy the second constraint, but not the first one. So if you try any combination of x1 and x2 for this problem, you will see that you will not be able to find a solution for this problem that satisfies both constraints. So that's why we know that this problem is infeasible, but the two-phase method, phase one is also showing you, but the method is also showing you that that's the case, because in order for you to find a solution, you need to rely on this artificial variable that is not part of the original problem. So in summary, how do you show that a problem has no feasible solution using the two-phase method? Well, you perform the phase one iteration or the phase one. And if at the end after performing the simplex steps, if the optimal tableau for phase one is showing an artificial variable in the basic variables, and that artificial variable is not equal to 0, then that means that the problem is not feasible. There's no solution for that problem, which is the case for this one. So that's what the problem wanted to show. Or that's the answer for this problem. And then finally, we have this problem that's for sensitivity analysis. I give you all this information. And also I'm giving you this formulation for the problem. So after solving the problem, we find the optimal solution. And if you remember, the optimal solution for this problem was x1 equals 20 and x2 equals 60. We can find that from this. This is the sensitivity analysis report. So for x1 and x2, these are the final values. So x1 equals 20, x2 equals 60. And the optimal objective function, I mean, if you substitute 3 times 20 plus 2 times 60, this is going to be equal to 180. So the objective function for this problem is 180. So now we have the optimal solution. We have the objective function value for the optimal solution, and we have this report, which is the sensitivity analysis report generated by Excel. So my goal is for you to understand what this report means in order for you to gather insights. So what I'm going to do now is I'm going to use this report to ask you some questions, and this is part of your assignment. So So here are the questions with the answers. So suppose that the capacity of the finishing operation is 140 hours. How will these increase affect the optimal revenue? Explain and do not find the new optimal value. Okay, so what I want you to do first is to check whether or not that increase is allowed by the feasibility range. So if we go back here, we are talking about the finishing constraint, right? So that will be the first constraint. This is the finishing constraint. So, so for constraint 1, this is the information that we have. We have the final value. We have the shadow price. We have the right-hand side, and we have the allowable increase and the allowable decrease. Okay, so using that information, we have the right-hand side was 100. Based on here, we have the allowable increase and the allowable decrease. So for the increase, this is gonna be 100 plus 20. So this is 120. For the decrease, it's gonna be 100 minus 80. So this is equal to 80. So your feasibility range is between 80 and 120. So what that means is you can increase the right-hand side by 20 units and the optimal solution for your problem will not change. You can decrease the right-hand side of the first constraint by 20 units and the objective function value will not change. So the question is asking, suppose that the capacity of the finishing constraint is increased to 140 hours. If you check that and you compare that with the feasibility range, that is greater than this value, which means that it is asking you to do something that is outside the feasibility range. So the answer for this question will be, well, the proposed change is outside the feasibility range. So we will need further calculations to find the answer. And that's something that I'm going to explain you later on. But the idea now is you can use this to decide, okay, I can provide insight because it is within the feasibility range, but in this case, it's not. So we have to state that it is outside the feasibility range. So we cannot state how would that impact the solution of the problem. If we look at the second part, if the capacity of the finishing operation is increased from 100 hours to 110 hours, how would this increase impact the optimal revenue? Explain and find the new optimal value. So now we're seeing that increase, which is 110 hours, it is inside this feasibility range. So we can comment on that. How would this increase impact the optimal revenue? Okay, so for that purpose, we have to look at the shadow price or the dual price. Excel uses the shadow price instead of dual price, but they mean the same thing. So the dual shadow price for the finishing operation is $1 and is applicable in the range 80 to 120 hours. So the proposed increase to 110 hours falls within the feasibility range. Okay, so the feasibility range goes from 80 to 120. Hence, the increase in revenue is that dollar times the number of time periods that you're increasing. In this case, it's 10 hours. So you will make an extra $1 for each hour that you're increasing your operation. So in this case, we're going from 100 hours to 110 hours, which means that we can increase our profit by 10 hours times $1, which is $10, which means that the total revenue will be increased from $108 to $190. So in this case, if we end up doing that, if we end up increasing by 10 hours this operation, then we will make an extra $10, which will be added to the objective function value. So that's the answer for this part. Then part C.
I had a question.
Yes, sure. Go ahead.
For the first question, it says how will this increase affect the optimum revenue? Since we don't know how to do that yet, do we have to state that we don't know how to do it yet?
No, so yes, so the idea for this one is that you can identify that it is out of the range. So you can state it that like that. So we don't know how, I mean, we will need further calculations that we don't have those concepts covered in class yet. You can state something like that. But the idea with this question is that you can identify whether or not you can provide insight by looking at the feasibility range. Does that make sense?
Yes, thank
Okay.
you.
Okay, thank you for your question. So yes, going back to that question. So the idea is that, okay, I look at the feasibility range, the increase that is recommended is outside the feasibility range. So we know that if we go for that increase, our objective function, our optimal solution is gonna change. So we will need to recompute the whole thing. And we don't wanna do that at this point. So the idea for that question is that you can identify that the change is outside the feasibility range. That will require some extra computations, and we don't know how to do that yet. I'm gonna teach you how to do that. But you know that if you go outside that feasibility range, the optimal solution of the problem, which is 20 and 60, is going to change. It's going to be different. So you will have to recompute the optimal solution for your problem. As long as we stay within the feasibility range, we know that this optimal solution is not changing, so we can provide insight on how that will increase or decrease our objective function. So a suggestion is made to increase the capacities of operation 1 and 2 at the additional cost of $5 an hour for each operation. And the question is, would you advise that? So for the finishing operation, the additional revenue per hour is $1. And if you're gonna charge $5 an hour, you know that you're gonna be losing money, right? So you're not gonna make any money. If you are making an extra dollar, it's gonna cost you $5, then you're not making any profit. If we look at the carpentry operation and we look at the shadow price for that is also $1. So same thing, you're making an extra dollar for each additional hour, but you are charging $5. So again, you are not making any money out of that. So the answer for this question will be none of the operations should be considered for capacity increase, because you're basically losing money if it is gonna cost you more money than what you're gonna make. So that will be the answer. And then here, if you can increase the capacity of both operations, which operation should receive priority? Again, you look at the shadow price. In this case, the shadow price is the same. So both operations have the same shadow price, $1. So both will have the same impact on the total revenue. If for some case you have one that is bigger than others, if you look at the shadow price, let's say for the second operation, let's say that, instead of 1, this was 2, then you know that you are gonna make more money by increasing the time of operation 2. So in that case, it will be better for you to go for the second operation, but that's not the case in this problem. In this problem, both dual prices or shadow prices are the same. So it doesn't matter which one you choose, it will still have the same impact in the objective function or in your revenue for the problem. So again, the idea with this is that you can understand how to use the information in the analysis. If you look at the lecture for this material, I show you how to compute the reduced cost, the shadow price, the feasibility ranges for each constraint. So all that you know how to do, but I don't want you to spend time doing those computations in the exam. I'm more interested in knowing if you can use that information to make decisions and to gather insight. So that's why I decided for the exam to give you a report just like this one. And then I'm going to ask you questions about that report. For me, that's more important, more relevant. Any questions? So that's all I have for the review. Now you have time to ask me any questions about the exam, if you have any.
I do have a question,
Yes.
but it was further back on the big M method. I don't know if you what was that?
The big M method?
Yeah.
This problem?
Yeah. There's just one thing I didn't get completely was
Yes.
where would you place the artificial values after you figured out how many there are? Where would you put them?
After you figure out, so the artificial values, the artificial variables, the idea of the artificial variables, remember, they are not part of the original problem. The artificial variables are just there to help you find an initial solution. So after you have done that, then your goal is to take them out of the problem as soon as possible. So after you find that initial solution for the problem, then the purpose of the artificial variables is completed. So you don't want them to be part of your solution because the artificial variables are not part of the original problem. So, so in the case of the big M method, you keep them in a tableau, but you want to make sure that they are not part of the basic variables at the end of the solution, right? Because if they are not a basic variable, that means that their value is equal to 0. So they are not making a difference. They're not making an impact in your problem.
Okay.
And so
I was thinking more on like where would you place them? Does it matter where you place them?
okay, so placement in terms of the columns or in terms of the rows? Is that what you're referring to, or?
Yeah, in terms of the rows, I think.
Okay, so remember when you place them in the rows, that will be the initial tableau. They are going to be like R1 is going to be placed. So if R1 is part of the first constraint, then R1 will be placed first in row 1. If R2 is part of the second constraint, then it's going to be placed second. So R2 is placed second here. You see, R1 is placed in the first constraint, so it's going to show up as a basic variable for the first constraint. R2 is shown as part of the second constraint, so it's going to show in the second row because it's part of the second constraint, and the coefficient is going to show that. So the 1 is going to show up in the first row because R1 is part of the first constraint. The 1 is going to show up in the second row because it's part of the second constraint. So I don't know if that answers your question.
Actually, just looking at it again, I think I get it now.
Okay.
Yes.
Okay. If you don't, just send me an email and we can talk.
Okay.
Any other question? So remember, this review is recorded. So I'm going to post this in the modules today, so you can take a look at the video if you need to. So I'm going to stop the recording now.